a lot of different issues that we haven't been able to examine easily with the lens of system dynamics. Issues such as spatial layout, networks, issues having to do with multiple nested layers of modeling. So this marks the entry into the area of modeling where we're going to be spending the most time in this course, and one that's in very high demand. And for those for computer science background, that critically makes use of skills you will have developed in other courses, skills around object-oriented programming, software engineering, etc. And we're going to be diving into our first agent-based model today. Taking a look at how it functions and distinguishing that from what we've seen with system dynamics modeling. First, just a look back at some elements of system dynamics modeling and a look forward to where we're going now. You'll recall that we gave an overview to system dynamics that included notes on its focus on feedbacks as a fundamental shaper of behavior. There was a notion that the structure of the system determines the behavior. The fact that we have a first-order delay where we had a outflow from a stock, and that outflow depended on the value of the stock in a proportional way. That led to a certain defined behavior for that piece of the system. And in general, as we added feedbacks, new behaviors became possible. We saw stocks as key elements of these feedback. Every feedback includes a stock. There's some state of the system being modified over time. And these stocks represent accumulations, right? Flow into a stock, if that's all you've got, it accumulates the value of the flow. Mathematically, it integrates that flow over time. If there's a flow in and flow out, it accumulates and it's drained by the flow out. Stocks are these accumulations. They keep track of the state of the system, and they accumulate over time with the flows in and drain with the flows out. And we've seen that these models are quite graphical. They're quite easy to depict. And it turns out that that helps understanding of the models by a broad set of people. We saw in the last lecture, and I did, incidentally, that very day post extensive notes walking through solutions to finding the fixed points, the stationary points, the equilibria for two different models. You'll find it on the Moodle site. These sort of models admit to formal reasoning. We can do things like identify where these fixed points are. What are its long-term behaviors? And in fact, which of those behaviors are stable? Which of those behaviors pull back and are resilient? So if you disturb them, they respond by resisting and pulling back to the original situation. And which of them are unstable? They explode. You have someone fly in with Ebola and it spreads from 1 person to 2 to 4 to 8 and expands unstably. We can study that sort of behavior of a model, even putting aside particular parameter values, with a quite nice lens using system dynamic models. So system dynamics modeling has accompanied us, and we also saw how it could include, both qualitative factors and quantitative when we started out doing a sketch of a causal loop diagram. But much of our attention was on the stocks and the flows associated with them, right? So we have stocks, flows, and we can depict the relationships between them using this powerful language which is graphical and clues us into the structure of a model. We saw stocks determine the value of flows. Flows at a given time, they derive their value from the value of the stocks at that time. And then the value of the flows dictate the change in stocks over time, right? If we have 10 people coming into a stock and 5 people leaving, that stock is rising at 5 people per day. 10 people coming in per day, 5 people leaving per day, and it's rising at 5 per day, 10 minus 5, right? Value of the flows dictate the change in stocks over time. We specify the structure of the system, how the flows depend on the current state of the system as captured by the stocks. And the value of those flows determine the evolution of the stocks. And then we run the model to see what the implications are over time. In short, we don't write down what the model's going to do over time with a given stock. We don't say this stock will rise and then fall and then rise again according to some formula. Rather, that emerges from the model. It's an emergent behavior of the model that the stock changes over time in this way, based on the flows that impact it and how those flows depend on the current state. So we specify kind of how the change in the system occurs, and we simulate it out to see how the system behaves over time, how the values of the stocks change. And we saw that there's some formal analysis that could be involved. So system dynamics is a very powerful method. Allows us to capture dynamics of continuous variables. Those variables that we had, the number of people who are infected right now, the amount of money in a bank account, the water in a bathtub. These are continuous quantities. We can refer to them as sort of real numbers. And this sort of modeling is actually very amenable to very rapid model prototyping. An experienced model of this sort can whip out a model pretty quickly. It turns out that it can also be understood by people from a wide variety of backgrounds. If you give people a bit of pointers, they can kind of come to understand graphically what's meant by a model, even if they don't understand all the details. And I want to highlight the fact that we have been building in a programming language. These stock and flow models that we are building are written in a programming language. It is a graphical programming language for many aspects of it, stocks and flows. It has formulas if we drill down to them, but this is what we call a declarative language. Does anyone know here, particularly those from computer science background, what do I mean if I say something is declarative as a language? Well, many of you have worked with these languages, perhaps without realizing it. Anyone mention another declarative language that's out there? Okay, Scratch, I don't know so much about, but I believe that it is building blocks associated with things like for loops and if statements and so on. And it turns out that it's a simpler language, and it has that in common with declarative languages, but we still wouldn't call it quite declarative. C is actually also a language that has some simple beauty to it, but it is not declarative. Let me give you a declarative language. Anyone used XSLT? Style sheet transformation language? Anyone here use Excel? Yeah? The language you put in formulas? There. Say this cell depends on the sum of these other two cells, right? That's a declarative language. You tell it what relationships need to hold within this model. What depends on what in what way? This cell is, cell C1 is A1 divided by B1, right? You give it the formula that you want to obtain, that you want it to maintain, that needs to be the case, and it will take care of making it happen. It will take care of calculating the values in the right order so that that cell C1 is equal to A1 divided by B1, which themselves may depend on sums elsewhere in the spreadsheet, right? Right? So it takes care of that. So time was, when I wore a younger man's shoes, I actually was part of the Excel team. We were a 12-person team at the time, and I was contributing to the Excel code base, and I knew the guy who wrote the code that did the reasoning about how it had to compute in what order all those cells. Topological sort was involved, and that was implemented behind the scenes. People who use Excel don't know that there's a function called, well, back then it was called fdoaddep, but it was a function that went through and calculated, figured out the order things had to calculate in, and then allowed the spreadsheet to produce the right numbers. That's a declarative language, folks. You specify what relationships need to obtain, and it takes care of all the how. It takes care of figuring out how that happens. These type of languages are becoming increasingly common. Some of what you saw, how many people in here have taken 340? Couple? Yeah. You saw Haskell? We're using Haskell? Yeah. That has some elements of declarative language. You sort of specify this function. This is sort of what this function does, and there's a lot of details that are figured out. It's not fully declarative, but it's a functional language that has many features of declarative programming in it. There's many other languages out there which are nicely declarative. Think about a circuit language. You draw out a circuit, what's connected to what, and it takes care of all the details of how it's connected. Anyone here use Yahoo Pipes? Yahoo Pipes, you sort of rig up these series of filters and sorting tools, etc., online. You tell, one of the tools might be go read this thing from a certain website URL, and it reads in the data, and then another one might sort it, and another one might filter it by these characteristics, and you hitch these up into nice pipes. And it takes care of figuring out what needs to flow to what. There's many tools like this. And in fact, for those who were in my 214 some time ago, you would have used shell scripts and sort of strung expressions together in a way that allowed one to take the output of the other. And that had a declarative feel to it as well. You didn't have to deal with all the details about how data was passed along, but you knew that data would be filtered through each successive tool in succession and would emerge on the other side in the appropriate ordering. So declarative tools where you specify the what and not the how, are very powerful communicational tools. And indeed, system dynamics adheres to this tradition. It adheres to this tradition of kind of allowing you to characterize what are the relationships in the system. What are the stocks? What are the flows? How do the flows depend on the stocks? And it takes care of all the minutiae of making that happen. Okay? As a result, it tends to be very transparent. But today, our query is different. Today, we go on and we turn a new chapter. And we enter the world of agent-based modeling, which is moving in the direction of system dynamics in terms of declarative structures, but where many of you will find yourself feeling very at home in the world of object-oriented programming. Java, in fact, will be our tool. What are agent-based models? Agent-based models are going to consist of a depiction of one or more populations of what we call agents. These agents are individuated. They are particular things. These may be people. They may be vehicles, like a car or a truck. They may be vials of medicine. They may be houses. They may be companies. The particular instances of classes of things. And each of those agents is associated with some characteristics. It's associated with some parameters, some state. These parameters are sort of things that don't change much. They're characteristics that are more or less static. So for a person, it might be gender, ethnicity, might be someone's birth weight. And for the sake of a model, which is short term, we might treat their income as sort of a static quantity. But then there's going to be some components that are state of that person. These are things that are modifying, changing about that person, their age, their smoking status, the people that are connected to them in networks and their preferences. And then there's going to be a set of rules for evolving the state and conditions under which those rules apply. Those are sometimes broken out here. We have rules under which certain actions apply. So I sometimes distinguish here actions as sort of making making the system change. I'll, in fact, edit this as we speak and put down actions here, okay? Actions. And then there's a means for interacting between agents. Rather than a stock holding agents of a certain sort kind of clumped together, we're going to have agents who interact with each other through some mediators. And these mediators may be networks, that I'm in a network, a family network, a network of colleagues, a needle sharing network, whatever it is. Or it may be in a spatial environment that I'm in. I share this classroom with you. We have time horizons and characteristics associated with that time, for example, whether it's discrete or continuous in character. And we have some initial state of the model. Now, all of this sounds quite abstract. We're becoming and looking at a very particular case of this in a few minutes. Now, I want to contrast this with what we see with system dynamics modeling. In classic system dynamics modeling, you'll recall that we subdivide a population up according to state. So we'll take a population and we'll divide it into susceptible, exposed, infective, and recovered individuals, right? These different stocks are divided up. They're distinguished. It's organized according to the state of a given person. Do you see that? A given person's state is either susceptible, in which case they're here. They're exposed, in which case they're here. They're infected, in which case they're here, or they're recovered, in which case they're over here on the right. So in short, it's organized, it's subdivided up, it's broken into pieces according to state. And then each of those pieces keeps track of the number of people who are in that state, right? Are you comfortable with that? The number of people in each of these states. You'll notice here's the stock. What is this stock doing? Anyone tell me? To make sure we're on the same page. What is the stock here in the center doing? I don't want you to think all stocks have to be just subdivisions of the population. What is this stock doing? I'll give you a hint. Its inflow is the same as this flow here. So what's the job of the stock? What does the stock do? If the stock has an inflow, I mentioned it not 10 minutes ago. What does the stock do to that inflow? It does what to it? If you have a stock and it has a flow in, so here we have a stock and it has a flow in here with some value x of t. Who knows how this is computed? It's computed based on lots of things in the model. Some function x of t. This stock here, what's its value going to be over time? Good. Total. And what's the fancy way we write a total for a continuous quantity? An integral from time 0 to the current time of x of t, right, dt. That's what this stock is. It holds the integral of this. It's summing it up, but in a continuous way. This is a fancy way of writing a sum, right? It's big S. That's what it is, actually. It's a big S. It's a kind of distended S. So it's summing up. So this cumulative incidence, this is summing up the value of this flow over time, right? So here we divided up the model by and large, organized it according to people's states, okay? And we counted, for each of those elements of organization, we counted the number of people in that appropriate group. I want to contrast this with agent-based modeling. With agent-based modeling, we're going to have a population divided into people or other agents, and each of those people, so it's organized according to agents, it's organized according to individuals. And for each of those individuals, what's it going to keep track of? It's going to keep track of their parameters, their characteristics, their current state, what's their current situation for that particular person, who they're connected to in networks, their location, things like that. So rather than system dynamics, we organize a model according to state and count the number of people. The data we have is the number of people in each state. Within an agent-based model, we organize according to individual, and the data maintained for each of those units of organization is the parameters and the state of that person and any aspects of context. It's almost system dynamics flipped on its head or flipped on its side. The organization is different. Here, state is within each individual, and system dynamics state is what's used to organize the whole model. That's the building blocks of the model. Does that make sense to people? We'll go through and explore this in just a few minutes. So in a model, we're going to have a population, and we'll be putting it there. Probably won't build one up from scratch today, but we'll see this in a model. And then in a simulation, that population turns into many particular people, many particular agents. And each of these agents has some parameters. So they might have an ethnicity, a sex, and an income for each of these people in the population. And each of those people has some state. So, for example, that state might be illustrated with a state chart here. And this state chart will be defining more than just the state. It will actually be defining as well the rules for evolving it and the conditions under which those rules fire. The actions that change that state and the rules under which they will fire off. So we have rules about under what conditions someone, for example, completes pregnancy and becomes no longer pregnant. Which case, in what cases someone will die, for example. So within these state charts, we're going to pick an evolution of state. And the state charts can be quite articulated. This is a state chart very similar to the one we just saw in that system dynamics model: susceptible, exposed, infective, and recovered. And we're going to be drawing these transitions which describe the changes in that state, but the states themselves, for a given consideration, are captured with one state chart. And in general, I'll have several state charts. One that might be for my infection status, one might be for my education level, and one might be associated with my current employment status. So we'll use different state chart to capture a different aspect of my state, and I'm going to exactly say one state with respect to one simple state with respect to a given state chart at a time. We'll see later there's composite states, but for the most part, you're in one state of these simple states at a time. Okay? And we can divide up a model in this way with multiple of these state charts in a very convenient fashion. And it turns out that this will allow us to avoid a lot of complexities that would confront us if we were sticking with a system dynamics model, where in order to capture, well, let me ask you this. Suppose we had a system dynamics model where we had susceptible, infective, and recovered individuals, S, I, and R. We saw that before. But now suppose we want to distinguish people, males and females. How do we do that? How do we keep track of number of males who are infected, number of females who are infected? Same for susceptible, same for recovered. How do we do that in a system dynamics model? Anyone? Yeah, you have a whole other set. That's exactly the right word. Who spoke there? Great. John? Yeah. Good man. So we'd have male, susceptible, infected, recovered, and female, susceptible, infected, and recovered. And they're probably not solitudes. You know, a woman could catch a cold from a man, and a man could catch a cold from a woman, and so on. But basically, we have to double the size of the model, right? And not only that, we need to sort of consider all combinations. If we further want to divide it up by age, we'd need to, for each of these, divide them by age. So we'd have males of 0 to 4, males of 5 to 9, males of 10 through 14 years old. Same thing for females. And we get all possible combinations. With state charts, it's not so bad. And in fact, capturing aspects of this heterogeneity, capturing aspects of these differences between people. If we didn't have sex in this model at all, we didn't have people distinguished by gender, and we want to add that, how would we do that? Well, we'd add a parameter in. We don't double the size of the model. We just add a parameter to a given agent. Do you appreciate that? Just add a characteristic for that person. It doesn't double the size of the model like it does in a system dynamics model. Then we need a way of having these agents interact. And the way we're going to be looking at earlier is with networks like this, having people communicate with each other over networks. And it turns out these networks are a central feature of aspects of the world. We see networks in the human sphere, or collegial networks, so networks of colleagues, networks from your family, networks of fellow students in a class. But we also see networks, of course, joining computers, right? The internet. Internet structure has been studied as a network. We see networks of roads. We see networks of air connections between cities. And it turns out the structure of these networks has a huge impact on the dynamics of the system, its behavior over time. We're going to be seeing that. And it turns out that agent-based models provide us a very convenient way of characterizing these networks and seeing how they affect that dynamics. And the effect, ladies and gentlemen, is often profound and very helpful for understanding the behavior of systems in the world. Now, you recall that I motivated on our very first day this sort of modeling by referring to the fact that we're dealing with systems often where the behavior of the whole is greater than the sum of the behavior of the parts. It's not merely reducible to the pieces. By understanding the pieces, we don't immediately understand the system as a whole. We get surprise behavior, like traffic jams, that are in no way obviously reducible to car engines and wheels and chassis and the pavement. It's an emergent feature of a system of all these things interacting. And we saw that in system dynamics. Where did we see system dynamics having emergence? Where did we see behavior coming out of a system that we didn't program in? I'll give you an example. We saw it, ladies and gentlemen, in that bell-shaped curve associated with infection spread. Remember this? I hope so. I hope so. Hello? So we saw it with this, right? We saw that bell-shaped curve, the number of people infected over time. We saw it, here's time here. We saw it rise and fall. Remember this? Yeah. So this was an emergent behavior of that system dynamics model. We didn't, in no place did it program that in there. We made some simple assumptions about how my chance of getting infected as a susceptible depends on the people around me and their characteristics. We put in some simple assumptions about how people recover, et cetera, maybe lose immunity. And out of this came different structures. For if it was just a simple SIR, no recovery, no loss of immunity, we might see something like this. With a loss of immunity, we might see something where it rises and it sort of oscillates. Here, structure determines behavior. We have a loss of immunity here. But this was emergent pattern. It was something we didn't expect. And it came, ladies and gentlemen, mark my words, it came from the interaction of stocks and flows. We saw patterns over time from these models, right? Patterns over time, right? There's patterns over time from interactions of stocks and flows. Was it not? Speak, as if in a Greek chorus. It was. Thank you. I didn't even require the accent. So that's great. In agent-based models, we actually have a lot more flexibility yet, because we're not just dealing with stocks and flows. We can capture behavior over space, patterns over space, and over networks. We can also capture patterns over time, but we're not limited to them. We can reason, for example, how a disease spreads over the space, like within Saskatchewan, how rabies outbreak might spread, or over networks between people. So this is from a model built in this very class some years ago, model of behavior of mule deer here in the province. Mule deer in this province, regrettably, were infected by a very nasty type of disease called chronic wasting disease. And it's driven by, anyone know anything about chronic wasting disease? Anyone know sort of the main component responsible for it? It's called, begins with a P, ends with an S. It's prions. These are misfolded proteins. And it turns out that deer get infected, it's fatal, but they live for many years. And in the meantime, they shed infection on the ground. Other deer can get infected from eating grass that's been contaminated by that infected deer, or by rubbing noses or what have you. It came up from the States, and it infected an elk farm here in Canada, and it's spread now to the deer population at very serious levels. And this particular model was simulating deer moving around, contacting one another, and shedding prions on the ground. And running this model, we had a system dynamics model of this that was quite insightful. But by running this model, we saw the burden of infection was actually very, very well defined spatially. It wasn't just spread out evenly over the space. It tended to concentrate on regions where the deer had to go, for example, to drink water. The deer had to go to find grass or what have you. So we can understand patterns over space. We can understand patterns that form rings. You remember this from the very first day? Something like this. Remember that? Running it with rings, and the rings emerge. It's an example of an agent-based model and the sort of patterns we can get. Or we can get patterns over networks, where a bug spreads over denser areas of the network, but not over less dense regions, etc. Now, with these sorts of models, we have a real difference from system dynamics models in another way. We have what are called stochastics in this model. Anyone know what stochastics mean? If I say stochastics, what do I mean? I'm talking roughly about what? Stochastic. So I would say network traffic is quite stochastic. The hits to your network, if you're running a corporate site, the hits to your network will exhibit stochastics. What do I mean? They are random. They exhibit uncertainty, but not only random, not only they exhibit uncertainty over time. They may be bursty, right? You go for a long time, and then some tweet goes out about your site, and it goes viral, and suddenly you get a lot of hits within a short period. And hopefully your server is ready for it. And then there'll be low days and there'll be high days. They're uncertain over time. And it turns out that with these sorts of models, agent-based models, we typically, not always, but typically have stochastic models. And they capture factors in the world that are a bit stochastic, uncertainties associated with catching a bug, catching infection, about the vagaries of my movement and when I fall back into smoking or what have you. These models are very powerful because they help us understand the degree of uncertainty that results in terms of results of outputs of the model, but it does require running the model many, many times. It requires running it many times over. So for a single run, our model might produce exact results for that run, showing number of people who would get sick over time here, and the total number of cases that have occurred in richer individuals or poorer individuals. Poor on the right, richer on the left, for the number of cases. But if we run this model many times, we'll find there's some differences from run to run. And we'll find that actually this is just a sample from a distribution. From a distribution. The actual distribution might look like this. And any particular run is just one particular sample from that. And if we run the model, say, 100 times, we might get some clues as to what the distribution looks like. So there'll be some runs where most runs, they have a large number of lower SES cases among lower income individuals, but there'll be some where they have almost none because the infection dies out before it can spread. And similarly, over different runs of the model, we may get different results in terms of the number of people infected over time, shown here there on that graph. Okay, so we're going to be talking now about agent-based modeling. We're going to be going and looking at the vocabulary of agent-based modeling. And I'm going to ask you folks, you're mature individuals. You are capable of doing a lot of learning on your own, and rather than tutoring you on all aspects of this vocabulary in class, I'm going to be asking you to learn some elements of it on your own. And we can use the class for the things that are unique to that class environment. Building up more interesting models, talking about their behavior, reflecting on their essentials. So I'd like now to go on and talk about some elements of the ABM vocabulary, the vocabulary of agent-based modeling, as it's captured in AnyLogic. Okay? So to do this, to do it well, ladies and gentlemen, I would like to suggest that you, like myself, call up AnyLogic. Okay? And what I'm going to ask you to do is, so many of you will have to run that script, call up AnyLogic, and I'm further going to ask you to go to the Moodle site for this course. Okay? Go to the Moodle site, and you will find in the models area of that Moodle site, there should be a model there that is called Communicable Mobility version 3 with Networks. V3 with Networks, okay? And I'd like you to download that model onto your machine here. Now, where is the Moodle? Okay, here we are. So it should be Communicable Mobility version 3 with Networks. I'll look at the version that's closer to what you see. It's several sections down on the website. Models used in class, and it's the latest of these models. And if you click in it, you may see something along those lines. But I believe there should be a way here within this to do save link as, save link as and actually save it as a separate, okay. It's giving me trouble here. So there should be a way to download this directly from this site, and I'm trying to remember what it is. Anyone remember off the top of your head? What is it? Control S here to just save it as a file and give it the appropriate name, .alp. Thank you very much. Your name? Evan. Thank you, Evan. So .alp. So you can just save this because this is the text of the file. Does anyone recognize what this is? What are we looking at? XML. AnyLogic models are in XML, which affords some benefits to it. Okay. So open this up and save it. Alan, would you mind summoning the magician? Merlin? Okay, thank you. Yeah, right. Yeah, Winchell wouldn't do badly if Merlin's not available. Okay, so do people have this downloaded now? That's right. It's the last one in models used in class, and it's called Communicable Mobility V3 with Networks. Okay? Okay? Do people have it there? Okay. So once you've got that, I'd like you to call up AnyLogic and go and open that model that you've downloaded. Okay. And opening up that model will provide us a concrete example of many of these features we're going to be talking about in the next half hour or so. Okay. Okay, so this is taking a long time to. Okay, so I'm going to go open this up. There's Merlin. Merlin, I have a question for you on something that is admittedly rather distant from your sphere of responsibility. So this is Moodle, and these are AnyLogic files, and I would like to be able to save this, directly download it to my computer. And if I go and I click this, I could do, as Evan noted, I could do Control S, but there must surely be a way, a better way. If I go like this, I can do Save As, but it saves this, and I don't know if it's saving actually the HTML or.
I doubt it.
Yeah, you mean like open it and save? And so right click? Oh, do Save As?
Save as. Yeah, if you did that, that's honestly probably the easiest.
Okay, it still calls it .bin, but.
Yeah, change it to whatever you want.
Yeah, okay.
Yeah, that's probably the easiest. I can ask Carrie. It's an association with the browser, right? The file type association.
Exactly. Exactly.
Usually you shift click on it too.
If you click the. Oh, this guy here?
Yeah, that one. If you click this, it will download it. So I think that's something different. The way we got those, right? Click save link as.
Okay, yeah, save link as, yeah. I mean, it does it. It's just it has to be renamed. So there must be something that was frobbed for this one. Yeah, that's much appreciated. Yeah, sorry for the trouble. Okay, so people have this down? You're able to open it up? Okay, so when you try to open it, what happens? Okay. So the answer was proffered. Thank you. Your name? Tad. Tad proffered that if you have it do show all files, it will no longer be grayed out. On the bottom of the open dialog. Yeah. Okay. So as I understand Tad's comments here, basically, I mean it's different because you're doing it on Mac, but basically it's you do open and if you go there and you find the folder it's in, it will initially be grayed out, but by saying show all files, it will be it will actually show up and you can open it. Is that right, Ted? Basically. Yeah, like communicable mobility 3. Yeah. So basically, it was grayed out, and you can do all files. Yeah. Okay. Okay. So people have that open now? Okay, who needs McLeanian help? Okay. Alan stands vigilant and stalwart. Okay, anyone need Alan's help? Okay. Okay, so ladies and gentlemen, I'm going to close these other models, and I'm going to do close all to, what am I doing? Oh, man, I should have said close all others. Here, I'll load it in again. There we go. Okay, so ladies and gentlemen, let's go take a look at this model as a particular example of HBase modeling. So the first thing I'd like you to notice is that previously when we built these models, they consisted of a single sort of active component, to wit, main. Remember that? We just said main, and we would put our stock and flow models in main. People remember that? Okay. Now, by contrast, we actually have something else. We have a class, a person. kind of defines personhood or personness according to the theory captured in the model. Remember, models are thinking tools. They help us, the thinking processes. They help us think through the implications of kind of theory about how the world could be and see what the logical implications of that are. Much better than we could do if we had that theory in our head alone. And so here we have a sort of a theory of personhood for this model. So I suppose people were classified into three categories with respect to infection status: susceptible, infectious, and recovered. And suppose they further were characterized by being in motion at times and then arriving and then departing for a new destination. What would the implication of that be? And, we're going to go into a lot of detail in different models regarding what we might depict here. But suffice it to say, just as in system dynamics, where we had flows associated with formulae, each flow be associated with a formula, here we have an unambiguous semantics associated with each of these transitions. This transition is triggered when a message arrives at this agent, which is going to be how agents communicate with each other, to say, like, you're exposed to my bug. It'll be with a message, and it will transition from susceptible to infectious. Or, let's look at the one down here, from infectious to recovered. The fox has shown its tail. Huli Jojo Wei Ba, I think it is in Chinese, if I'm not mistaken. So this transition is a rate transition associated with, mark my words, associated with a rate of 1 divided by 100 as the rate. How long do you think it will spend on average? This rate transition is actually a certain probability per unit time of transitioning. Where have we seen that before? Where on this very blackboard have we seen that? Having a certain probability of transitioning per unit time, associated with what construct? Begins with an F. A flow. Thank you for putting me out of my misery. Good. Was that Evan or? Yeah, good man. This is a rate transition. It's a similar concept. Certain chance per unit time, and the rate is 1 over 100. What do you think the average time is that they'll spend? If I told you the time unit of this model was days, how do you think they'll spend on average in the infectious state? Oh, it says per minute. Excuse me. Oh, man. That's pretty quick. Okay. So how long do you think they'll spend on average in the infectious state? If a certain chance per unit time of leaving of 1 over 100, what's the mean time in that state? 100 minutes. 100 minutes. That's right. That's a pretty quick infection. We should go and modify that sometime, but for the moment, we'll live with it. So a lot of the concepts carry over from system dynamics modeling. That concept of memoryless transition. No matter how long you spent in this infectious state, you have this certain chance per unit time of leaving if you're still in that state. That's what this is saying. And we can encode similar concepts here. But there are some things, ladies and gentlemen, that are going to be new. For example, over here, in this in-motion state, we have a timeout transition. After exactly this time, every exactly 1 minute, it will be sort of reforming the network. Or, when we click on this state itself, when we enter this state, whether through this initial entry or by coming back here, we move to a certain location that's chosen to be my current location plus some perturbation, plus some sort of change around it. And we move to this, start moving towards this new location, okay, towards this new target, this new destination. And then when we arrive, we will then enter the state again and choose a new destination. You'll notice that here's something familiar. What is this thing? Where have we seen this before? What is that? What lies before you?
Parameter.
It's a parameter, indeed. It's a parameter. And a parameter, like in systemdynamics model encodes an assumption, and it's important to emphasize it actually communicates that assumption. It serves two purposes. It encodes the assumption and also communicates that assumption from the point of creation to the thing being created. And we'll see that in a minute, okay? So let's go back now to main. Double-click on main. And now we'll see some additional elements of the AnyLogic modeling vocabulary. One thing is two more parameters. Parameters that relate to the model as a whole. The population size, for example. Or here, the communicable distance, which would be the same per person. There's this thing, report infection count, which is some sort of, it looks like a lightning strike, but it's actually what's called an event. It's really an event schedule that every 1 minute will print out the number of people infected. And you'll notice we ask this population, we ask the population, how many people are infected you? Let's go take a look at the population. Take a look at this population here. Here we have a population of size this many people, and they have this sort of magnitude for them, this sort of magnitude of movement around their current position. And we're going to place the agents at a certain location. And here we've defined a statistic about this population that says, if you ask me how many count of people are infected, if you ask me, hey, what's your count infected, I will count up the numbers that match this characteristic. Oh my gosh, that's the most horrible thing, and I stand remiss. I stand almost ashamed. Get rid of that semicolon. It's not needed there. This, ladies and gentlemen, is not a statement. It's an expression. It's something that computes a value, right? Is certain person asking their infection state chart, is this certain state active? And what's the state? Whether or not they're infectious. Okay? Buzzing, blooming, confusion. I'm not explaining a lot of this right now, but we'll be coming to better explanations for quite a few pieces of this in coming lectures. My goal here is to just get you exposed to some elements of this vocabulary. So having been fortified by that exposure, seeing some things familiar and some yet unfamiliar, let us now run this model and marvel. Okay, so we're going to go run this simulation first here. And let's go run that. And right now it's running in kind of slow motion. What do we see here? What do we see? People interacting. Those people are red if they're infectious, green if they're not. And what causes one person to become infectious? A person to go from susceptible to infectious. What is it that causes that? Proximity. They're nearby each other. You could see some right there as these hit each other. Watch that one. Boom. Right? They form these transient networks as they pass, and that allows the bug to spread from one to the other. It's kind of as if we're walking in a bus station past each other, and I sneeze, and you become infected. So this model is simulating this kind of movement of these two types of particles or two types of people, and each of them is kind of jostling about randomly, but they're infecting each other. In fact, some become recovered here. Now, we're watching this in slow-mo. Let's speed it up, right? We can go and watch this considerably faster. In fact, we can watch it at a much faster pace. For those of you who are interested, you can zoom out or zoom into it by doing Control Roll Out or Control Roll In of the mouse. You pull that and zoom in and out. In a model like this, we can examine the effects of spatial factors in a way we can't very easily with a system dynamics model. I'm going to do this now for a much larger population. Where, from whence is that population number defined? It's defined here. Population size 100. Population size 500. It's a property, as in the system dynamics model, of the experiment. So let's run this. Let us run a large population. Let us run a population where we have people densely connected. Well, as you can see, it spreads very quickly and completely. On the other hand, if you have a very small population, let's go create a small one, right? Go right-click. Well, you could just go do, there's no reason to do that. Do new, experiment, and you can say, you know, small population here. And in the small population, make the population size just 10. And we can run it now. And you could, you know, ask questions. How long does it take till 75% of the population is infected? What's the average distribution of times until they're infected? What fraction of the runs does it infect everyone? You could ask questions like this. In this case, it looks like everyone recovered. You could ask questions, how does the density of the people within the space determine how quickly the infection spreads? What's the relationship between density and the speed of infection spread? These are the sorts of elements that can be examined within a model like this. So let's go, having seen that, let's go talk about some elements of the AnyLogic ABM vocabulary. Elements that I'm going to ask you to familiarize yourself with over the next few weeks so we can do neat things with this model without me having to tutor you on each little element. In contrast to system dynamics, we're going to be working here with a much bigger modeling vocabulary. System dynamics models basically had a few small, simple building blocks that we used in creative ways to build up a model. So we had stocks and flows, and then we had some somewhat higher level structures. Things like first order delays, aging chains, these sort of successive stocks in a row that captured progressive sort of aging within a certain context, progressive amounts of time within a context. But fundamentally, with stocks and flows and some auxiliary variables and parameters, we could do a lot. A very small modeling vocabulary, great power. By contrast, agent-based modeling is a different beast. There's lots of different pieces that we're going to be confronting. Lots of different types, elements of that alphabet that we'll be seeking to master. So here are some of them. Parameters. We've seen those before. Events. Really, event schedules is what they are. Sort of schedules, you could say, this event will fire every day, and maybe it will do some reporting. It will save something to a file on disk. It will save something to a database. Maybe it will count up the number of people with some characteristic and print it out. Or maybe every day it will perform some action to reduce the number of people that are infected. We're going to see that there's multiple mechanisms for describing dynamics in agent-based models. What we just saw were state charts, these state charts that characterized evolution of a person. Very similar to UML state charts. Do they still teach you UML elements in 270? Did you see that? Yeah. So quite familiar. We could alternatively have custom update code that changes things when you enter a state of the model, or when you leave that state, or when you make a transition across one of those transitions, cross a transition. We can also, it turns out, have stocks and flows in this model. That would be a hybrid model. We have stocks and flows within the agent-based model. We're going to have populations in these models, a population of people or of deer or of cars or what have you. We have agents that communicate with each other, sending and receiving messages most commonly, although they might communicate with stocks and flows as well. I have a flow out of something into you. Maybe it's a belief in some idea. So here we're going to have messages exchanged between agents for them to interact. And we're going to have multiple sorts of transitions associated with the state charts that we have that govern their change over time. We saw that earlier when we had, for example, within the context of this person, their timeout after a certain fixed amount of time, and there's a condition transition as well. So many types of transitions associated with agents in the model. Okay, and these transition types will be used within our models for different purposes. We have connections and networks. Agents make and break connections. I didn't show it to you, but if you go up to main here within this model and you go scroll down in main, you will find that there's an area of main called space and networks that defines the networks applied to certain populations. In this case, it's that whole population. And we said we wanted a distance-based network with a certain distance sent by communicable distance, okay? And what that means is that if a given pair of individuals, A and B, lie within this distance, they'll be connected. Otherwise, they won't be connected together. So we're going to have these networks, and these networks can be dynamic or static. We actually made them dynamic in this case. That was accomplished by this. You may remember this transition here applied the network. In other words, it says, hey, make this network happen, and it will figure out for each pair of people, are they connected or not, and draw it accordingly. Connect them accordingly or disconnect them accordingly. So this network was changing over time, and that network existed when people were close together, okay, when they were within a certain distance. Turns out that we'll see subtyping. Subtyping in the sense of subclassing includes subtyping, although it's conceptually distinct from it. Subclassing is one way you can have subtyping, but it's not quite the same. You can have this thing implementing an interface, and it's a subtype of the interface without it being a subclass. There's spatial embedding. We can put individuals nested within cities, so people within cities and cities within a region. So we can have a multi-level model. We've seen mobility and movement with this model, people moving around in various ways. Graphical interfaces to this. We'll be seeing data output mechanisms associated with it, and we'll see that there's a lot of stochastics. So when we run this model time to time to time, we may run it in a deterministic way or a fixed way. If you go to a given experiment here, let's say large population, and we were to scroll down, we would find that we could either run this model in a unique simulation runs, or we could run it in a way that's totally replicable with a fixed seed. This will dictate whether when we run the run once and we run it a second time, whether we'll be guaranteed to have the same results. If it's random seed, we're not guaranteed the same results. If it is fixed seed, we will be securing the same results out of it, as long as no input data has changed, etc., as long as it's the same model. So we're going to see these stochastics play a significant role in certain tasks like calibration of the model, trying to match historic data, sensitivity analysis with the model, and interpreting the results of scenarios. We're going to see that there's some further distinctions between how messages are delivered, whether it's immediate or in an asynchronous way, that each one just has a queue that they come up on. And we're going to have to reason a little bit about the concurrency aspects of the model. Different agents are evolving in parallel with each other. And we'll see diverse types of agents. Often we have more than one population. So we might have a population of people and a population of companies, for example. And they might interact in certain ways. So these are some elements of the AnyLogic modeling vocabulary that we'll be using specifically for agent-based modeling. And we are going to try in the next few sessions to build up a set of simple agent-based models that will illustrate, ladies and gentlemen, some principles. they'll illustrate some aspects of agent-based modeling. So, with that in mind, we have a few minutes yet. Are there any questions about this, or would you like to spend the remaining time here building up a simple agent-based model? How many people, so who would like to ask a question? Okay, you want to build a model? What do you think? Okay, let's go build up a very simple model. We only have about 10 minutes to do it, so this is going to be about as simple as it can get, but it will be something that will orient you to the basic pieces. Okay. So, ladies and gentlemen, I would like you to close this model now, and we won't be saving that. And I would like you to go to File, New Model, and Alan, start your engines. Okay. Okay. And you're going to say first ABM, okay, and I'll put in CMPT 394 fall 2015. Okay, we're going to set the model time unit to be days. Okay, actually I'm going to make it years. Excuse me, make it years and say finish. Okay, okay, great. So, ladies and gentlemen, what I'd like you to do now is, having done that, we have this model just like we did before for system dynamics, but we're going to take a sharp departure now. Having built this, we're going to do right-click on it and say New Agent Type, and I'm going to declare this to be a person. Okay? Are people comfortable with that? How did I do that? I right-clicked on the model as a whole. I said New Agent Type, and I typed person. Are people okay? Who needs Elenian help? Okay? Okay. So, ladies and gentlemen, we are going to proceed quickly and expeditiously with this. Okay, the first thing I'd like you to do is to go over to the palette, and I would like you, ladies and gentlemen, to go down to the place here that's called presentation. And we are going to lend this person, each such person, an appearance to dignify them. Is that okay? Okay? So I went to palette, I went down to this presentation area on the left-hand side, and I'd like to drag in here an oval. Now, many of you may want to use a nicer picture than an oval, and you are welcome to do so. But as I say, I'm proceeding expeditiously. Okay, so I drag that in here, and I centered it on this point here, which means their visual depiction will occur at their logical location. If we put it to the right, this oval to the right, their picture would appear to the right of their logical location within the model. So we're going to put it here. Okay? Are people comfortable with that? Okay. Okay. Let's continue our frugal modeling here. Having done that, that was in person. Please note that that's in person. Make sure you've got the right canvas open. This is a key rule of this sort of modeling. It's very easy to drag it into the wrong one. Make sure you put that in person. Okay, double-clicked on person and open that. Now let's go back and double-click on main and watch this. This will be a key step, ladies and gentlemen. Mark my mouse. Okay? I'm going to drag in person into main, and I will do two things here. Three once I frob one of them. I will type population instead of person. You could also do that in the properties, but then clicking on this, making sure population is selected. Secondly, That's just a naming thing. Naming is very important. It's not to be minimized. Having done that, down in the properties window, I would like to go from a single agent to a population of agents. So this does not represent just one agent, but a population. Notice when I did that, the icon changed. Notice it's like this without brackets, and now it goes to with brackets. And finally, ladies and gentlemen, I would like to change the initial number of agents to 250. Okay? $250 agents. Okay. Now, two rules of modeling. Number one, save it. Control S. Number two, build early, build often. Up here in the builds, we'll prepare it to run. So you want to do a build up here to build the model, and you'll notice it says build completed successfully. Okay? Having done that, ladies and gentlemen, I'd like you to go right-click on simulation and do run. And yes, I know running it would have built it anyway, but building is a good habit to get into just to make sure there's no mistakes you've introduced. Okay, so now this came up, and we're going to run it. And it'll be disappointing. Up there in the upper right is this little oval. From whence did that oval come? Who defined that oval? You did, indeed. But you'll notice that up in this navigation area, if you drag it down, you'll see there's 250 different people. The problem is they're all on top of each other, which sounds both unfortunate and uncomfortable. So we're going to go and change that. Humor can help prevent sleep. Okay, so we're going to go up and change that, okay? We're going to go and have these appear at different locations. So, ladies and gentlemen, I'd like you to go back, stop that run, go back to main, and go down main, and actually, excuse me, I'm going to do it a better, more robust way. There is a way to do it for main, but I'd actually like you in main to click on population. Let's make it more explicit, okay? So click on population, and I'd like you to drag down, and I'd like you to go to this place where it says initial location within population. Do you see that? Do you see that? So I went open main, and within main, I went down to the population here, and I scrolled to the place where it says initial location. And I'd like you to say in the specified point, and for the X location, I'd like you to say uniform between 0 and 500, and the same thing for the Y location. Okay? Are you okay with that? Are you okay with that? So what did I do? I went to main, I opened main. Clicked on population. I scrolled down to that initial location. I changed this to say in the specified point, and I made this uniform between 0 and 500. Anyone want to hazard a guess for what that means? That's right. And it's a continuous random variable, it turns out. So it could be 232.5924, right? Yeah, okay. So, ladies and gentlemen, shall we run it? Run or not? Good. Run. Okay, so there we get something like that. The agents are defined before us, are they not? Do you see that? Okay, so ladies and gentlemen, let us proceed expeditiously. The minutes count down. We're going to have to get out of here very soon. But I'd like to do something a little bit more. So double click on person, go to palette, and now let us crack a new area of the palette. Let us go to click on the agent palette here, okay? And I'd like you to drag a parameter to the agent that's called income, okay? Income. It's in person. We're giving the person an income, okay? Good question. Appreciate it. Okay, so ladies and gentlemen, I'd like you now to, having done that, I'd like you to go and just double check that this income will put a default value of 0, okay? And I would like you to now go and go back to the main area, okay? And we are going to go to population. And you'll notice now within main, income now has a formula here for a person's income within population. And we are going to put in something else in place. Ladies and gentlemen, we're going to put in place a draw from a log normal distribution with, so we're going to do a log normal. And remember, control space is your friend here. And we're going to put in a log mean of 11, a sigma of 6, and a minimum value of 0. Okay, so this means it'll be drawing from what's called log normal distribution. The log of it will be normally distributed with mean 11, standard deviation 6. And the minimum value drawn from this will be 0, but we don't have to worry because it's always 0 or more. It's in fact always going to be greater than 0. Okay. Okay, so what this means is each person in the population is going to have an income that's drawn from this distribution. Let's run this thing, okay? So I'd like you to run it here. And nothing seems to change, but let's go down and go to this navigation. You'll find that each person here is associated with an income. And there's a fair gap in those incomes. This first person on mine is associated with an income of $700 million, whereas the third person is unfortunately, well, excuse me, the fourth person has only $5,000 income per year, presumably. Okay, the final thing we're going to do right now, ladies and gentlemen, because time is a-ticking, is we will go back to person and we will set, I'm doing sort of a glimpse of several features of AnyLogic. Go back to person and go click on the oval for that person. Do you find that in person? Go click on the oval. And I would like you, ladies and gentlemen, to go scroll down until you see the area position and size. So again, we're back in person. Click on the oval, scroll down to position and size, and there'll be a place that says radius. Do you see that? Okay. I would like you to go click so it changes from an equal sign to a sort of little arrow here. And I'd like you to put in place here something that says log, L-O-G, okay? Actually, it should be 5 times the log of income plus 1.0. Okay? So an income of 0 will be of radius what? An income of 0 would be of radius log 0 times 5. What's log 1 times 5. What's log of 1? 0. But successively larger incomes will have larger radiuses, but in a logarithmic way. So now let's run this model, ladies and gentlemen. What do you think we'll see? Okay. Yeah, we'll see a population. What are these small ones? People with. Okay. Well spoken, Garrett. So that's right. These are particular lower income individuals. Now, if we wanted to, we could go add some additional features. It wouldn't be hard to add a state chart which would have people moving back and forth between states, but we're out of time. So I've given you a glimpse about building a model. I've walked you through some steps to have a simple model. What remains is the dynamics of it, the change over time. So we've seen how we could impose a heterogeneous population, spread them out over space, associate each person with this characteristics, associate them with a visual representation, and have that visual representation declaratively specified to just equal their income without actually writing a lot of code. And that is the mechanism we'll be using in coming weeks to build up models, okay? So that's all for today. Thank you very much for your patience, and I will recommend that you watch a video or two prior to our next class. I didn't require video today, but I may ask you to review 2 videos prior to next class, okay? Thank you. Hi. Yeah.